So what if you were to take one word to describe the, I don't know, the focus of this chapter, what would that one word be?
Dissolving.
Okay?
Solubility.
Okay. Anybody else? Good. I would have said solutions,
Dude, that's what I was thinking.
well, then open your mouth and say it.
I was literally about to be like solutions, but then I was like, no, that's stupid. And then you
And the
said
heading of the chapter is properties of solutions. Okay. Now, dissolving is a big part of that. Solubility is a big part of that. That's a good one word, big picture of what we're doing in this chapter. Okay. So now what we're going to do is really start getting into today some of the unique properties that dissolving a solute does to the solvent properties. Okay? So essentially the main point of today is if I have pure water versus water that I've dissolved something in, do they have the same properties? They don't. In fact, they've got quite a bit different properties, and we're going to talk about a couple of them today. Oh, that's further than I wanted to get to, but we'll put that up there anyways. Okay, I want you to open up your book. We're going to look at a couple visuals in your book, page 509. We're going to continue talking about this interesting topic of vapor pressure. Okay, so liquid solutions have physical properties significantly different from those of the pure solvents. A common example you may have heard of is antifreeze. Does anyone know what that means?
It doesn't freeze. It's against freezing.
Okay, but what's its purpose? Where does it go?
It keeps the engine from freezing. Keeps the water from freezing in the engine.
Okay, so in your engine you've got water that essentially acts as a cooling mechanism for your engine. Okay, well we know that water freezes at what temperature?
0 Celsius.
0 degrees Celsius or 32 degrees Fahrenheit, correct? And so under regular Iowa winter conditions, what would happen to...
Freeze.
Yeah, your engine would freeze and that would cause a lot of problems. Okay? And so what they do is they put this antifreeze in, and that's just a fancy word for it. That's what they call it. I don't know what exactly it's made up of, but essentially what that does is it allows it to lower the freezing point of your water so that it doesn't freeze as easily, and really won't probably ever get cold enough to freeze.
Would it also lower the boiling point though?
It raises the boiling point.
Oh, it makes it farther away from each other?
It has to do with how vapor pressure works.
Okay.
We'll get into it as we progress, but to explore how this works, let's consider an experiment. You can see the little experiment at the top of, did I say 509, right? Yeah, top of the page at 509, where you've got a sealed container that encloses two beakers. One, we're going to say, contains sulfuric acid solution, which would be just water with dissolved sulfuric acid in it. And the other one is just your pure water. Okay? Over time, gradually the volume of the sulfuric acid increases and the volume of the water decreases. Okay? Eventually it gets to the point where, as you can see on the right side of that picture, what has happened?
The water turns into the solution.
Okay? This should bring back at least a little bit of memories of something we talked about, I don't know if it was last chapter or 2 chapters ago, a very similar idea. Do you guys remember?
Yeah, the melting thing.
Yeah, the whole idea that solid melts to form a liquid and it happens through what phase? Yes.
Still.
Mind-blowing, right? And then we also talked about why that was. Do you guys remember why that happened, or what was the result of that?
Vapor pressure off of the solid and liquid somewhere else.
So you got your two beakers. Okay, let's say this has ice, this has H2O, liquid. So I mean, that's dumb.
Ice. This also has ice.
Liquid water. Okay? And let's say we're above, let's say we're 40 degrees Celsius. What would you know would happen?
Didn't know.
The ice would melt, right? Okay? But if you remember, the ice that was sitting in here, now we had an enclosed container because that's. Oh.
For sake of
Emily would be
future
proud.
classes,
Darn
he
it,
made that
Emily's
shot.
not here.
He made that shot for sake of future classes. He made that shot.
Okay, and common sense would tell us that this would melt here and then you'd have some liquid at the bottom, right? But that wasn't the case in this enclosed chamber. What we actually saw was that this started to happen, correct? Okay, and the reason why, if you can remember, is it had to do with the vapor pressures of these two. Okay? What was happening is the vapor pressure of this was high, and the vapor pressure in the liquid form was lower. What that meant is this was trying to spit off a lot of gas particles to increase the vapor pressure, right? Remember that? And this, as this was spitting out to increase the vapor pressure, the liquid was saying, no, I don't want that much vapor pressure, so what was it doing?
Turning into liquid.
It was absorbing it, right? And so it never did reach equilibrium until what happened?
They're both liquid, or one was.
It was, yeah, completely, the ice completely changed to liquid form, because if one's giving up, the other's taking it in, are they ever going to reach equilibrium until it's all completely gone? No. This is the same idea for solutions. So, let's go back to your book here. All right, the vapor pressure of the pure solvent is greater than that of the solution. That's the only way that something like this is going to happen. If the vapor pressure of the pure solvent is greater and the solution is lower, what you're going to see is the pure solvent giving off vapor and the solution absorbing that vapor until, just like the situation we talked about a couple chapters ago, one gets completely transferred to the other. Okay? So we can see this. The bigger question then is why? Why is this the case? Okay?
The aqueous solution has really low vapor pressure.
Yeah, the question is why though does it have a low vapor pressure? We can make that deduction based on what we see from an experimental result, right? It's from what we know, what we see here in this little experiment, the only thing that would make sense would be that the vapor pressure of the solution is lower than the vapor pressure of the pure solvent.
It's really cool, actually. I like the water on these.
I know, it is. It is. I think it's one of the more fascinating things. So, I think it's up there. Yeah. At the very top bullet, it says the presence of and this is really what's important here, non-volatile solute lowers, no, that's not what non-volatile means, lowers the vapor pressure of the solvent. So non-volatile just simply means it's not likely to evaporate into the gaseous phase. Okay? Does this mean that if I dissolve salt in water, salt has no vapor pressure? No, it just probably has such a small amount of vapor pressure in its solid state and due to its properties that it's very unlikely to contribute much, if any at all, to the overall vapor pressure of the solution.
So why do you smell things? Is it like little tiny particles?
Like smell things is usually due to gas
I mean, yes. but
that's diffusing through the air.
If you're in a cave, is it moisture that's carrying the tiny bits of whatever rock it is? Is it, you smell that?
Well, I'm not sure if that. Yeah, I don't know exactly what you're smelling, but yeah, if you're smelling something, it's because gas particles are coming into your nose. You know, whether it's of it from the vapor pressure or what? Yeah.
Weird.
But like you can smell bacon, right?
Yeah. But like, I'm thinking like seawater. It smells salty. Is it because
I've only been to the beach like once, so I don't know.
I've only been once or twice as well, but it smells salty. It smells gross. But
Yeah, it might have something to do with that. I don't know for sure. Okay, so let's talk about why this is. So if you look, I'm going to start reading, but it's going to have to do with that visual at the bottom. You can see the left visual is the pure solvent, and the right visual is the one where you've got some solute dissolved, and that solute doesn't contribute to the vapor pressure. Okay? I'm going to start with, I think in the middle of the paragraph, the very middle of the whole reading, it says a Y. Did everybody see that? Right in the middle, on the far left side. Okay? Because we can explain this observation that the vapor pressure of the pure solvent is greater than that of the solution, which we kind of come to an understanding on. Under these conditions, the pressure of vapor necessary to achieve equilibrium with the pure solvent is greater than that required to reach equilibrium with the aqueous solution. Thus, as the pure solvent emits vapor in an attempt to reach equilibrium, the solution absorbs it in an attempt to lower the vapor pressure towards equilibrium. This process results in a net transfer of water from the pure water through the vapor phase to the solution. The system can reach equilibrium vapor pressure only when all the water is transferred to the solution. This experiment is just one of many observations indicating that the presence of a non-volatile solute lowers the what? Okay. The rest of this is kind of me explaining, okay, why does adding a solute lower the vapor pressure? And you can see where this is probably headed, because doesn't vapor pressure have a big impact on boiling and freezing? And so you can see where this is leading to and how antifreeze lowers the freezing point and raises the boiling point, which we'll get to in the next couple lessons. Okay? We can account for this behavior in terms of a simple model shown below. The dissolved non-volatile solute decreases the number of solvent molecules per unit volume. Everybody hear what I said? Let me read that again. This is the why. The dissolved non-volatile solute decreases the number of solvent molecules per volume. If I were to rephrase that, I would just simply say, because of the solute, there is less solvent to produce vapor pressure. Does that make sense? Per unit volume, you have less water molecules that are going to give off vapor, because the rest of it is your solute, which isn't very volatile, so it's not going to contribute to the vapor. Does that make sense? You're probably wondering, well, wouldn't it eventually reach equilibrium after like a bunch of the water molecules transfer to, why does it have to all evaporate? Well, just because you start losing the volume, doesn't the pure water still have the same number of molecules per unit volume, whether it's this much volume or this much volume? If you have less volume, you also have less what? Molecules, right? So even the decreasing the volume doesn't change the vapor pressure of the pure solution. It actually keeps it exactly the same. Okay? So let's keep going. And it should proportionately lower the escaping tendency of the solvent molecules. For example, in a solution consisting of half non-volatile solute molecules and half solvent molecules, we might expect to observe vapor pressure to be what? Half. Since only half as many molecules can escape. So if I have half things that don't really give off any vapor pressure and the other half does give off vapor pressure, if we were to compare two things of like volume, so like volume, pure H2O solution, but this solution is a 50-50 ratio. What do I mean by that? Yeah, 50% solute, 50% solvent by volume. I would have half as much water here as I do here, correct? Which would make sense that I would have half as much vapor pressure because I have half as much things that can give off vapor.
Okay.
That makes sense? Okay? Then it goes on to say, in fact, this is what is observed. Okay, then it goes on to talk about Mr. Raoult's law. Okay? What he did is he took this idea and he put an equation to it, and it's actually quite simple equation. So this would be the pressure of the solution as it relates to the pressure of the pure solvent. So this would be what the vapor pressure of the solution is. This would be what you would typically see the vapor pressure of a pure solvent to be. And what do you think this has to do with the whole situation?
The amount of volume that is the solvent.
What was that?
It's the amount of the volume that is the solvent.
Yeah, so like if I have a 50-50 solution, what's this going to be? 0.5.
4.5, yes.
So it would make sense that the solution vapor pressure would be 0.5 times the pure solvent's vapor pressure, or half the pure solvent's vapor pressure. Does that make sense?
Yeah.
Okay? So, that's your problem.
So in that experiment with like the ice and the water on the tubes, if it was a container full of water, a container half or 25% full of water, would they over time equal out as well in containers because of the vapor pressure?
We're adding another variable into the equation, so
yeah.
I have to.
Or is it the same surface area?
Well, the water, I think it would probably be the same because we talked about how whether you have this much volume or this much volume, the vapor pressure from the pure solvent is going to be the same. Because you have the same amount of molecules per unit volume. Therefore, the same amount of vapor per unit volume.
So it would happen.
I think you'd see the same thing.
Okay.
Okay? So let's look at this problem. It says calculate the expected vapor pressure at 25 degrees Celsius. Okay, and it tells us what we're doing. We're taking and dissolving that much grams of table salt into, you guys remember what a cubic centimeter is equivalent to? Okay? Okay, and it gives us the density of water. We can almost, in other problems, we're just going to say that the density of water is 1. I don't know why they actually give it, because on other problems you kind of have to assume the density of water is just 1. So just keep that in the back of your memory bank. Okay? So, we have to essentially, based on Raoult's law, what's the main thing we're going to have to figure out? Because essentially, the other stuff is constants.
Pressure solution.
Like how much of it is solvent, how much?
Yeah, so we got to find the mole fraction. Okay, because I think in this problem we're assuming, trying to find the vapor proof. We're solving for this. This is always a constant, guys. Does that make sense? Okay, and I believe they gave it to us. Yeah, right here. So the vapor pressure of your pure water at 25 degrees Celsius is going to be that. Now we know that at 40 degrees Celsius it'll be higher than that and so forth, right? But it's a constant at that specific temperature. Okay? So we need to figure out, in order to find this, what two things do we need? What makes up that variable? How do we find mole fraction? Yeah, mole part, mole total. Okay? We don't have either, do we? Okay? But we got enough information to figure it out. So we got 158 grams of table salt. That gave us the molar mass of our common, not table salt, wow, not table salt at all.
Sucrose.
Sucrose, sugar, table sugar.
342.
Table sugar. Okay, 343.3 grams for every 1 mole.
A little under half mole.
Looks like it. Gives you the actual number. Sake of time, as always. 0.4616. Wow. Wait, that is how you spell it. Sucrose. Okay? How would I find the moles of my water then? A little bit more difficult here. Not much, but a little bit.
You have to use the density.
Use the density and,
It gives you the water.
okay, so yeah, we are gonna use the density, but that's not gonna give me moles. What will it give me?
That'll give you grams.
And then,
Convert.
yep. So we know that we've got 0.9971 grams for every 1 milliliter. And we could add our second conversion here to convert grams to what?
It's 18.02.
Yep. Now you're going to see here that, ouch, most of the solution here is going to be made up of your pure water.
35.6.
What do you get?
35.6 moles per whole water.
Okay. Part overhaul.
That's almost all of it.
Yep.
98% of it.
Yep.
199 grams. 88.7. The solvent, wouldn't the solvent be for 35.6 over the total?
Oh,
So that's the solution.
yeah.
You can find that too, you should subtract 1.
Yeah. Sorry, Chris. My mistake. Kelly, what's our answer then? You better get it.
9.9873.
Okay, that gives us our solvent mole fraction, which tells you, okay, how much of this solution is really just your solvent or your water, because that's going to be the volatile portion of your solution, so that we can figure out how much this is going to be lowered. Now, in every case, adding a non-volatile solute will lower your vapor pressure of your solution. The question is how much lower it will it be based on your mole fraction. You guys are probably way ahead of me already, yeah? You're looking in the book.
Yeah, yeah. My notes are in my book, which are somewhere. Oh, I'm off the top.
Yeah, that's another reason why I say reading the book is pretty helpful, because most of the stuff, the problems we do is right out of the book, so that, you know, if you miss something or you lose something, or when you're reading through the book, it's supplementing what we're talking about in class. It's on the same wavelength. Okay? Annie, did you get the answer here? Yeah.
Mm-hmm.
So, not a lot lower, but it shouldn't be a lot lower. We really didn't dissolve that much sugar in comparison to the amount of water that we had to begin with.
Minus 0.34.
All right, let's do this one. This one's a little bit different. We're going to have to take, and I'm going to have to give you one little caveat for how to do this type of problem. It isn't exactly the same. There's a little subtle difference, and I'll explain why. Now, we're kind of introducing a principle with this problem that we haven't completely introduced yet. And what that principle is a colligative properties. You probably remember hearing that word because it's kind of one of those, I don't know, rememberable words. But what colligative properties is, it's talking about effects of solutions, or different properties that you have of solutions are going to be dependent upon how much particles you have dissolved, not the size of the particles. Now that seems a little bit goofy here. So the problem we previously did was covalent. What is an important thing you need to note about the difference between how covalent things dissolve and how ionic things dissolve? You guys know the difference? Have we talked? I don't know if we've talked about it, but I'm just curious. Can't remember.
I mean, ionics have to be separate.
Yes.
Oh,
Okay. So the previous problem, we dissolved a covalent thing, which doesn't break up into more particles. So when you're using ionically bonded things, the amount of particles it breaks up into does play an important role.
Inspired by like.
It's not that, yeah, we did this idea in like chapter 4 when we did solutions in chapter
Yeah,
4.
I remember from last year.
Yeah, but this is going to be significantly easier than that.
Okay, that was frustrating.
Yeah, I remember that there's like.
Okay, same idea,
So
35.0 grams of a certain ionic compound here. I want to get that to moles because the predominant factor dealing with this is how many particles you have from the mole ratio, mole fraction. What do we got? 42.05. I hope I started that. Did I go back and
Yeah,
start
I
it?
remember you going back there.
Yeah.
Okay. I don't remember that vividly. Okay? We only got 6 minutes, so I'm sure you just love that I just give you the answer to these.
Why don't you put much more?
Okay? And it does tell us it's water. It didn't give us the density, so we could technically just use the density that we used last problem, but to make things easier, we're just going to assume the density is 1 for water, which is really nice because then I could take 175, wait a second. It's already in grams, isn't it?
So you just gotta do the moles.
I just gotta go to moles. But if it was 175 milliliters, a lot of times you could just assume that it would be just 175 grams. Probably don't even at this point have to show all that work. You guys have done so many molar mass conversions.
I heard your grammar saying, don't show your work.
Well,
Tell the freshmen. If the grammar is saying, done enough, don't show your work.
well, they don't listen to me anyway, so.
That's true.
Okay? So, this mole number is the amount of moles of the whole entire thing remaining intact. Okay, well, we know that it doesn't remain intact, and so we got to figure out how many particles it's going to break up into so that we know how much it's going to inhibit the ability of your volatile thing to vaporize. So, how many particles will this break up into?
3.
And that will give you 0.738 moles. Okay, then to finish this, you would do what? We got 9.71, 9.71 plus 0.738.
10.448.
10. Oh, the answer of those two added together.
Yeah.
Okay? Should give you 0.929. That's uniless. So we have a little greater impact on the vapor pressure, but not a ton more. Six. And there's your answer. So what's the big thing you need to remember when dealing with ionic versus covalent things dissolving?
Multiplied by the number of particles.
It breaks up into, because the impact something has on the properties of a solution is 100% dependent upon how many particles you have, not how big those particles are.
How did you know to multiply by 3?
What?
How did you know to multiply by 3?
Okay, this is going to break up into 3 particles, 2 sodiums and 1 sulfate
Oh.
ion. Okay? Now this should also make sense when we throw salt on the ground to get the ice to melt. What we're essentially doing is creating a solution which lowers the vapor pressure, which therefore lowers the the freezing point, making it essentially melt at a lower temperature. And this is why they don't use NaCl. They use a different salt instead. Part of it is, you know, part of it's cost of it, part of it is safe for the environment, but why would this be better from a chemistry standpoint, based on what we just talked about here?
Because the,
Specifically,
oh,
we talked about
breaks
here.
up into more.
It's going to break up into more particles, so it's going to have a greater impact in inhibiting the vapor pressure of your solvent, thus making it actually freeze at a lower temperature and melt quicker, or at a lower temperature.
Is that as many as it can get? Is 3 as big as it can get for emulsifying? Because,
No. No.
okay.
You could have like aluminum oxide,
Oh,
but like
okay.
that's not going to be like economically affordable and probably not extremely safe for the
Yeah,
environment.
it'd be
either.
weird.
Yeah. Okay. So I'm kind of getting a little ahead of myself talking about freezing point depression, things like that. But
Well, aluminum oxide wouldn't be stable though, would it? AL
why not?
03?
Al2O3.
Oh, AL, okay, yeah.
Yeah. Okay.
That was that.
So the only thing that I will say, this is just a modified version of Raoult's law, and it's not a ton different. Just let me explain kind of the main difference in when you would use this equation. You can kind of get rid of that part. You would just have P total is this and this. This is just basically taking two parts of Raoult's law and adding them together. And the situation that you would need to use this is when you have a liquid-liquid solution and both liquids are volatile. Okay? So what's important about that? So solution would really be the pressure of A plus the pressure of B. So let's say I have an alcohol water solution. Right? They both have a certain vapor pressure, correct? They're both volatile.
Yeah.
Make sense? Okay? If I had 50% alcohol and 50% water, you would expect the solution's vapor pressure to be what? Halfway in between both.
Yeah.
So like if I had water, I'm just giving you numbers, they're nice, easy whole numbers. If water vapor pressure was 20 and alcohol vapor pressure was 10, and you had a 50-50 ratio of both, you would expect to have a what? 15, okay? Now if you had 80% water, you would expect the vapor pressure of the solution to be closer to the water's normal pure vapor pressure than alcohol's pure vapor pressure. Does that make sense? Okay. So this is the equation you're going to use if you have two volatile solutions. Right? Done.